Okay, and we're back. Time to save the world with a little bit more formal theorem proving, which is pretty cool. So we were working through the arithmetic section a little bit, and we did add, subtract, multiply, and divide. And then these ones are just combinations of add and subtract and multiply and divide, and then summary combines all four of them together. Then you've got the order of operations section, which is like, plus, minus, divide, and multiply. Which order should you do them in? And then there's exponents and parentheses and stuff, which I don't think is so interesting. I'm not sure that's such a formal proof thing. And then fractions, we could work on the fractions section, but like one part of that is that you just write all the expressions using the primitives that we've already got. So, if you're working with 5/4, you just write 5 divided by 4 and then have some expression using that. And metamath, as you've kind of seen already, it is quite a lot of hard work to do algebra. And so trying to get all those fractions if you have something with uncommon denominators, trying to get the denominators to be common is actually quite a big thing. So my suggestion is we leap over that. If anyone really wants to see some fractions, then drop a comment. You can always do that. But in lieu of that, I think it'd be cool to move on to something a bit more abstract. So let's try a bit of number theory. I think that's kind of like an interesting idea of the aliens like, okay, well, maybe you know a bit of basic arithmetic, but do you know any number theory? What can you do? Okay, so let's talk about a divisibility test. Is 32 divisible by 4? Well, I think clearly 32 is 8 times 4. But press the wrong of these buttons, one of them will destroy a city. So you've got to work it out. So one way of starting with this is to go to metamath. You can start off on the main website, us.metamath.org, and then have a look at the proof explorer, and then have a look at the theorem list. And here we go. So let's have a search for divisibility, elementary properties of divisibility. So that's pretty good. So let's have a look in that section. So here are some proofs. So the first one, interestingly, is that it's got this section for proving that the square root of 2 is irrational. And that's just an absolutely classic ancient theorem, which is really, really cool to see that in the database as a kind of landmark of what's possible with mathematics. And then we get on to the divides relation. So this is a divides relation. And here's a pure definition of it, where it says you have two numbers x and y, where x is an integer and y is an integer, and there exists an n, which is also an integer, such that n times x equals y. All right, so that's pretty nice. And then it's got some alternate definitions. So you can also have m divides n if and only if there exists an n member z such that same. So this is the same kind of idea as that, but it's just kind of stated in a little bit of a simpler way. And I think quite a good one, I had a little look earlier, and quite a good one to base our proof on would be something like this, right? So if k is an integer, m is an integer, and n is an integer, right? And k times n equals n, so that's not going to be too hard to prove, right? If we've got 8 times 4 is 32, we can probably already do that. Then that implies m divides n, okay? That's the result we're trying to get, is m divides n, right? So let's have a go at that. So that's called DVDs 01 lem. Okay, so QED, I want 4, and I don't know how to write divides. I wonder if that's correct. So is that the question it was asking us? Is 32 divisible by 4? So does 32 divide 4? Is that right? Contains a pass error, huh? Okay, so the question we're trying to answer is, how do you actually write in metamath notation? Like, what is this symbol? Rather than in processed, is one of these a way of seeing that? Because I kind of don't want it in that. Oh, copy formula to clipboard. Yeah, okay, let's try that. Okay, yeah, so it is this. It's this double pipe symbol, which I think is what I did. I think maybe part of the issue is that it doesn't want brackets. Just close those down. Is that better? Step incomplete. Okay, so let's see if it's happy doing that. Okay, so what did I have? This DVDS01 lem. Let's get that out and see whether we can do that. Okay, so this would establish that 4 divides 32. That is what we need to show. Okay, so we've finished it all. And I think the number we need here is 8, because we've got to show that 8 times 4 is 32. And then, okay, so we need to prove that each of these is true, and we need to prove this is true. So what I would suggest is let's have a crack at that directly. So let's have 900. 8 times 4 equals 32. Ah, bizarrely, that's actually in the database itself. I'm very surprised because some of these other multiplication problems we haven't done, but that seems to be right in there. So we have this, right? And so now I think it might actually be possible just to leap straight to here. Oh wait, maybe it's not. No? Okay. So we should maybe add in some of these. Okay, so let's see if it will accept those as... Can we do that? Yeah. It's very weird that it's not automatically proving 8e.zz, right? I think we can probably do 8e.cc. I think that must be in there somewhere. So 8 is a complex number. 8zz, 8 integer. Like why, if 8 is a complex number, why can't you say that if 8 is complex, we know that 8 is complex, 8 is, well, that's not true, is it? No. Okay, it's the other way around. Yeah, that's a mistake, isn't it? So if 8 is complex, it doesn't necessarily mean it's an integer. It could be pi, you know? But if it is a natural number, then it's definitely... so that's what nnzi will be, is if it's a natural number, then it implies, which is I, it's a integer, 4z. Okay, so can I get 32 e dot nn? Loving it, loving it. Okay, so it's happy that 3 is a counting number, 2 is a natural number, therefore 32 is a natural number, therefore 32 is an integer by the same argument, therefore all 3 of these things are true, right? And therefore we've proven all 3 of these at this conjunction at the same time, and we've proven this, right? And so therefore this will stand, right? And therefore this conclusion is true, 4 divided by 32, which is great. And one thing that's really interesting about this is just this, 3pm 3.2i. When you see that with pm, okay, and it shows you here, it's the 3 things combined. That means it's from the Principia Mathematica. So if you know Russell and Whitehead's like classic text in logic from the early 20th century, all of the Principia Mathematica theorems are proven, I think often by Norma Gill. Does it say who proved it? No, it doesn't say there. In fact, let's look it up. That would be a good... wait. What was it called? 3pm3.2i. 3pm3.2i? Yeah, Norma Gill, 1995. So this is right back in the beginning of the project. Norm started the project in the early 90s, and actually 1995. So this is one of the really basic ideas, is that if you have 3 things which are true, the conjunction of them is true. And it's just really interesting that it's proven using one of these others, PM3.2i, which is that's then for 2 implication rather than 3 implication. And this is an interesting one, which is a definition of 3 things conjuncted together. And there's an argument that having it in this form is superior. Anyway, getting distracted. Maths is too distracting. So I think, yes, 32 is divisible by 4. Good. Okay, that's very good. Strict mathematics. So let's get onto an advanced question. 192 divided by 9. And in a way, this isn't any more difficult, right? So if I get rid of this, and I get rid of this, and I'll have another pure one of these, and I will get rid of this, get rid of this, and I want 192 divided by 9. And I think the answer is false. So that's quite interesting because 180 will obviously divide 100, will divide 9. So 198 will, but not 192. So for example, if we do 192 divided by 9, 21.3. So it's not true. Okay, so that brings us to another thing, is that if I set off trying to prove this, the problem is that I'm not going to be able to prove it because it's not true. And so I'm going to get stuck. But what is the opposite of divides? So we need to kind of have a look around. Is there a definition of not divides? Anywhere here? Or can we negate the statement? Can we say it is not true that n divides m? You know? I'm not exactly sure how to do that, which is kind of an interesting thing. We're getting into some logical deeper water here. We might get stuck, but what is the point of doing this? So yeah, you know, that's an interesting one. Not equal to, but it's not divides, which is what I'm looking for. Yeah, okay. No number between 1 and m minus 1 divides m. That's an odd lemma because you'd have thought that would be false. Interesting. Maybe there's conditions on m. But okay, so this is not m divides n, right? So that's how they've done it in the database. So let's, which was it? It was a structured version maybe? So let's have a look at how they've done that. So if I just do Control U, okay, yeah, it doesn't, it removes the proof. So they've just done this dash dot, which is the equivalent of not. So this dash dot is the way of representing this symbol, this not symbol. Okay, so I want dash dot. Is it with brackets? No. And it's interesting to think about how to prove it, because I don't think this dvds01lem is particularly useful, because that establishes that this is true, but it doesn't. We're going to need an if and only if statement. Like, how have they done it here? So yeah, it's stuff like this, right? Where no, that's not quite right. See, this is quite good. If m divides n, that implies m is less than or equal to n, and then they show that that's not true. But we are going to need an if and only if division statement. This is getting interesting. Okay. So maybe this. A is a natural number, B is a natural number. B divides A if and only if A divided by B is a member of N. So if we could show, that might be an attack, is that if we show that A divided by B is not a natural number, that would be okay. Let's go right back to the start of this section. Same thing here for integer. Same thing here for mod. But like, I don't exactly know how to work with n mod m in such a way. Okay, I'm going to try this. I'm going to try this. dvds val 2. Okay. Let's see what we can do. Right, so I am saying 9 divides 192 if and only if 192 divided by 9 is an integer. right? And then let's try and pull this out the front like we did before. You happy with all of these? Yes. So if we have 2100, I think 9NN should be enough for that. And I think 9, what we want is 192 e.nn, nn. Loving it. Okay. So we've proven this, which is good. And then we get this relation. So that's 4,000. One or more grammatical typos, hey? Okay, so maybe this double-headed implication needs its own brackets. It does. Awesome. Our friend axiom modus ponens there, making an appearance. So, what we need to do is prove, so this is where I want to go, right? I want to say this is not true. It is not true that that is the case, right? Because then it will... What is that, huh? I wonder what this E slash is. Does it mean like is in the complement of ZZ? Yeah. That's not... It's in the complement of ZZ? But that will be enough to establish the result, right? So we've done everything we need to do, except for we just need to prove that 192 divided by 9 is not an integer. And I have no idea how to go about that. Like where... Like what? Like what? Like what is going on? Okay. And what... I've never even seen a symbol before. That's really fascinating. That's a great symbol. Okay, so let's just see if we can have a look around. So theoremless contents, not an integer. Integers, upper sets. Finite intervals, elementary interval functions. Okay, well maybe this is less interesting to sort of be recorded. I don't know if I should stop the recording and sort of come back to you when I've got a better result. But I think let's try integer sets. Integers. Yeah, so that's what we were using before. So if it's natural, it's complex. If it's natural, it's art, it's real. If it's natural, it's complex. 1 is natural. Principle of mathematical induction, eh? Some properties of specific numbers, special number properties of non-negative integers. Okay, I am going to call it there. I am completely stuck. But what I will do is I'll save the proof as, what should we call it? It is not 9 divides 1 is 2, and we can come back to it. So thank you for tuning in, and I'll see you in the next one when hopefully I can get past this roadblock. All right, bye.